But we can read also as it is.
Okay. All right. Okay. Yeah. Sorry. This is probably the best I can do. Should I go ahead or should I wait?
Okay. So it's a pleasure to introduce the next speaker today. Is Feng Xu from University of California, Riverside, and is going to talk about rigorous results about relative entropy in quantum field theory.
Okay. All right.
Okay. Thank you.
Okay. Thank you. First of all, I'd like to thank organizers for inviting me. Sorry that I wasn't able to. In fact, I wasn't able to ask a question earlier. So maybe I should start by asking Tom a question first. My question before was that there is this. You said there's this diagonalization trick, diagonalization using some numerics. I'm curious. What kind of program do you use, or is it something straightforward? Hello?
So, are you asking a question to Thomas?
Yeah. Sorry. Am I making it more complicated?
Yeah, I hope it is still around. So let's see.
No, that's all right. So yeah, I'm sorry. No, don't worry about it if it's not around.
Okay.
Sorry, what?
Okay.
Sorry, I missed that. I was like,
sorry. Yeah. So I was interested in computing this entropy. So you said that there's some you guys use some numerics, some diagonalization to compute those entropy, non-entropy for type 1 algebras. So I'm just curious, do you use some kind of program, or what is it something more sophisticated than I thought?
No, it's not that. It's mathematical.
It's mathematical. Oh, okay.
Yeah, it's just mathematical.
Well,
yeah, I mean, if we wanted to push it, like right now our matrices are just like 40 by 40 by 40. If we wanted to push it more than that, we might need something more. But I mean, I mean, the difficulty is just doing some integrals, really. So it's not diagonalizing or anything. It's just
how is that compared to what Cassini and his collaborators did? They're doing this on lattice, right?
Yeah, he does it on the lattice. I think they have many more lattice points than we have, but we don't need to go to that high. Yeah.
All right. Okay. Thank you. Okay.
Yeah, but yeah. Sure.
Okay. So yeah, I guess I should get back to my talk. Thank you. Okay. So yeah. So I'm going to talk about some of the recent work. So you see the list of reference here. The first one is joined with Vergata. Some of you might have heard my my talks on similar subjects before, and I apologize if I have to repeat myself again. But I hope to emphasize on slightly different aspects of this story as I go along. We'll see how that goes. So let's see. Let me turn on the page. So I'm going to be talking about some motivation and main results, and on list. And as I said, I'm going to just at least have them on the screen, and then I will select some topics. So let's go to motivation main results. So I guess many of you are aware of this now. So recently, there's been enormous amount of work by physicists concerning entanglement entropy in quantum field theory, motivated by many connections. So we have heard Tom's talk before. So for mathematician, there's some basic questions about those computations. So for instance, we know the entropies you computed infinite. So I think the singularity structures sometimes the cutoff independent quantities of most interest. So I guess I should move this hand here. Okay. So often the mutual information is argued to be finite based on some heuristic physical argument. And in fact, when you can actually derive the singularities of these entropy from the mutual information by taking singular limits. So from a mathematical point of view, I think this mutual information or relative entropy, a kind of independent quantity is of fundamental interest. Okay, so but immediately one faced with the following question. So because the relative entropy is well defined, it goes back to work of Araki back in the late 60s and early 70s. So there's this immediate mathematical question. If you start with Araki's definition, can you actually check this relative entropy is indeed finite, right? This is, I thought, sort of the first question you might ask, and we think this is sort of a fundamental question. So we began to address some of these questions in the last few years. So let me mention that before that there's also work by Hollands and Sanders, and who wrote a very nice article on the subject. But in our case, we need to prove certain relative entropy as defined by Araki is really finite. So the proof is actually quite interesting. So so maybe I'll just say the words, but not go into details. So use the convexity and the theory of singular integrals. Okay. And these quantities have been computed before by physicists using, for instance, replica trick. I think it's a major open question for mathematicians to turn this replica trick into mathematical theory, and that seems to be hard because I know even for the models coming from statistical mechanics, there's this long series of paper, trying to justify rigorously replica trick, but that seems still be work in progress. But anyway, so we have to do this without finite integrals and so forth. I guess that's good news to some people, but on the other hand, that's still open question. Anyway, so let me describe the results. So for the free clarinet, this is what Tom described at the end of his lecture. Just free fermions. So let's say we have R free fermions, and we take two intervals, and this mutual information is given by this formula. So R is the number of free fermions, and so when there's one fermion, so that's called that's a Dirac Formula. So this is -1/6 logarithm of eta. Eta is a cross ratio, and in this case we have chosen this cross ratio to be less than 1. So the usual one is -1/3. That's because you have the it's not a chiral theory, it's the full theory. So there is a left mover, right mover, so it's doubled in that case. But I think this is a fundamental case. But anyway, sorry, I should turn the page. Okay, right. So what's the big deal about this result? I have to say that actually it takes a lot of efforts to prove this. So anyway, so the one thing about this result is that even though some of you may wonder, well, what's the big deal, right? You prove this here, prove these finite results for free fermions. It's a free theory. But once you have the relative entropy defined in the sense of Araki, many nice consequences of this result. So for instance, one such result is that because relative entropy is monotonic, so if you pass to a subalgebra, it decreases. Okay, so and then if you have finite index extensions, it follows also the relative entropy is bounded by the index computation. So then you see that almost all the chiral CFT would follow that have finite relative entropy. I haven't defined relative entropy yet, but I'll probably do that in the next few transparencies. So let me just say the results. So this includes large family. In fact, it includes all the known examples color CFTs. Okay. So theorem proved this. This is sort of more or less consequence of the results, and then we also connect the relative entropy and index of subfactors in an interesting, unexpected way. So I should mention that this connection is different, but related to the Pipsma-Popma result that connects Stromer entropy to index. Okay? And I should say that back then there's also a little bit of surprise, right? It's usually postulated that the mutual information of pure state, such as vacuum state for complementary regions, should be the same, but in the Carroll case, it's not true. Okay, so it turns out what happens is that in fact, in this case, the fact that we have type 3 factor is important. So the violation in this case is measured by the global index of the Carronite. Okay? So I haven't defined some of the terminology here. It's probably familiar to some of you, but not all. But I guess I'll try to define some of these notions in a minute. But let me just go ahead and describe the results. Right. So the violation I was talking about earlier turns out to be the logarithm of the global index, and in physics literature, this is also known as topological entanglement entropy. Okay. So yeah. So we have a precise formula about this. I should say that the connection to topological entanglement entropy is not. So far is numerically seems to be related, but there's no conceptual explanation yet. So this, I should mention that this is the entanglement entropy defined by Katayev and his collaborators. Okay. Anyway, so let me see. Right. So that's the main result, and I like to move on to the notion of entropy and the relative entropy. Yeah, sorry, because of the time, I'm in a different time zone, so I missed the earlier talks. So I'm not sure if this has already been discussed, but please bear with me. So I want to give a short introduction to entropy and relative entropy. So the phenomenon entropy is the quantity associated with the density matrix. So this is the formula. So it's minus trace rho log rho. Okay, so this is a non-negative quantity. It can be viewed as a measure of the lack of information about the system to which one has the state. Okay. Now, this interpretation is in accord, for instance, with the fact that the phenomenon entropy is greater or equal to 0, and a pure state has a vanishing phenomenon entropy. Okay. So pure state has the least phenomenon entropy. So it's because it's a state which is defined by 1 over n identity matrix has the largest phenomenon entropy, which is the log over n, the dimension of the Hilbert space. Okay. I make a comment here that phenomenon entropy is nonlinear because of this log rho here, right, in the state. So in general, it's not easy to compute even in finite dimensional cases, such as those, some statistical mechanical model finite lattices. Okay. So I think it's fair to say that every time you compute some quantity like this, it always gives you something interesting. You have to find a technique to compute this, and the result usually says something about sometimes surprising about an underlying system. Anyway, so that's phenomenon entropy. Now, actually, mostly I will focus on the notion of relative entropy. So this is defined for two density matrices, and it's given by this formula. So this rho and rho prime are two density matrices, and so this is trace rho log rho minus rho log rho prime. Okay. So once again, this is non-negative and can be infinite. Okay. So one way of thinking about the relative entropy is to think of the sort of measure the distance between rho and rho prime. In fact, this is equal to 0 if and only if rho is the same as rho prime. Okay. But it's actually not a distance because it's not symmetric with respect to rho and rho prime. So if you switch rho and rho prime, as you can see from this definition here, it's not symmetric. So sometimes people just symmetrize this. In other words, just S rho prime plus S rho prime rho and divided by 2, and use that as a sort of distance measuring the distance between two states. Okay, so that's relative entropy. And a nice thing about the relative entropy is that, in fact, previously I've defined this for matrix algebras, right? And so this is for B of H. But relative entropy is, in fact, can be defined for arbitrary Polynomial algebras. So this is what I said earlier. It was defined by Araki, and it's formulated using modular theory. So here is brief description. You have two fixed normal states on Polynomial algebras in standard form. You choose the vector representatives in the natural column, and then the anti-linear operator. So the relative modular operator, the relative operator here, and you do the usual modular theory. You get the relative modular operator, and so I should say that if these two states are the same, of course, this is the usual modular operator, and sometimes referred to as modular Hamiltonian or reduced density matrices and so forth. Anyway, so yeah, so that's the modular operator, and Araki defined this relative entropy to be like this. It's the correlation function of logarithm of this modular operator in the state defined by the vacuum. Okay, and of course you can extend it in positive linear functions, which are not necessarily states. Okay, so I'm writing the formula here just to give you a sense that there's a formula. I mean, it's defined for arbitrary states. Okay, using modular theory. But of course, this is well defined. It has some properties which follow more or less directly from the definition, but it's not very easy to compute. Yeah, so maybe, yeah, so that's what makes the replica trick so amazing. Physicists frequently can do this computation, so that's quite amazing to me. But anyway, so let's move on to, so yeah. So what I'm going to say next is that, to just next two transparencies, I would just show that this is indeed a generalization of the, the relative entropy I defined before here for type 1 for non-algebra. So this is what the next two transparencies is about. So if you take type 1 for non-algebra, you take two states that correspond to density matrices. So here's the description of what the modular operator looks like in terms of the density matrices, and you just plug into the definition of Araki, you recover exactly the relative entropy defined for type 1 states. Okay, so that's one. And there's another example. If you consider bipartite system, so you have tensor product of two Hilbert spaces, the observable algebras factorize, and you take a normal state on this tensor product Hilbert space or on this observable algebra, and you do what's called a reduced density matrix. You trace over, in this case, reduced density matrix for region A. You trace over Hilbert space associated with B, and similarly you define row B, with A and B switched. Okay. In this case, the mutual information, which I mentioned before, is given by this equation. This is a very very nice equation. So it tells you, in some sense, measuring the distance between this general state and this. So general may be tangled, but this is untangled state. So it sort of measures the distance between them, and this. So this is the mutual information. Okay, this, in this special case. If you just go through Araki's definition, in this special case, you get this is equal to it's related to non-entropy in this way. Okay, and of course you can also do for tripartite system. You have tensor product two Hilbert spaces, three Hilbert spaces, and then you just use the fact that relative entropy. I'm going to say a few words about the relative entropy in the next few transparencies. But this is from the property of relative entropy, in particular the monotonicity of relative entropy, that is a decrease when it passes the subsystem. Then you get immediately what's so-called strong subadditivity for non-entropy. Okay? So this is actually very important inequality. This was originally proved by Lube and Rossky, but follows rather easily from monotonicity of relative entropy. So I think this way of formulating this strong subadditivity I mean, in my opinion, it's probably the best formulation. Anyway, so yeah, so these two transparencies just show that, you know, how Rocky's general definition specialized to to the type 1 case, which is most cases in the quantum information theory, and some of the inequalities follows rather naturally from the general properties of relative entropy. Okay, so let's see the next one. Right, so yeah, so I want to advocate a bit about Kosaki's formula. So previously, I have given you the definition of relative entropy using a relative modular operator. Okay, and some of the properties are evident from that definition, but some properties are not so evident. So what I like about this Kosaki's formula is that some of these properties follow rather directly from the formula. So in general, it's desirable to have a formula for this relative entropy in terms of states. So without making reference to the modular operator that, you know, is sort of derived from the states. So this is provided by Kosaki, okay? So let's look at this formula, okay? This is a pretty ugly looking formula if you see this the first time. But I claim that after you stare at this for some time, you begin to see the wonder that's in the formula. Okay, so here's the relative entropy as defined by Rocky. Here we got in this formula we got two soup here. Okay, the first soup is over all the positive integers. Okay, the second one is over xt plus yt equal to 1, where xt is a step function valued in the polynomial algebra M is equal to 0 when t is sufficiently large. So in other words, this is just, you know, just a finite number of points in M, right? So it's a step function. We say it's a step function, but you just assign, you know, it just pick finite number of elements in M. Okay, so here's the quantity. So we take a logarithm of M. M is the M here. And then you do the integral from M inverse to infinity. So when M is very large, you should think of M very, very large. This is approximately 0. And here is the state, the dependence on the two states. So you have omega xt star xt, 1 over t, and then omega prime yt star, 1 over t squared. Okay, so you see that this, you know, these weights are different. And also you see, well, what's yt? Yt is 1 minus xt. So, but you also, I want you also pay attention to where the position of the star is. And the first one, the star and the star in the second in the second state are different. For those of you who know modular theory, you know that's because you know for the type 3 factors, you know, we have the states, you know, all the intricacies associated to modular operator is related to this the position of the stars. Anyway. Okay, so that's the formula. You got two soups, and in practice, of course, this is not very easy to compute. But of course, if you're a supercomputer, you have enough elements of the phenomenon algebra. You know enough about the states on those elements. You should be able to do this computation. But anyway, this is a complete general formula. And what I like about this formula, I'd like to share with you, is that many properties of relative entropy follow easily from Kosaki's formula. Okay, so I will describe a few examples. So for instance, if you take two normal states, phi and omega and c here on the phenomenon algebra, and denote by omega 1, c1, the restriction of the state to phenomenon subalgebra, okay? Then you see that immediately the relative entropy decrease, okay? This is the property I was mentioning before, right? I mentioned it before twice. The first one, we use the fact that relative entropy for free fermion is finite, and then we can immediately pass to the subalgebra. And then there's also gives a very nice proof of a strong subadditivity property for phenomenon entropy. Okay, so how is this proved? Well, if you just look at this formula, you immediately see that it's true, because when you restrict the subalgebra, this soup you're souping over is, even though this, I should say that, even though this looks like an integral, but remember, this is a step function. So effectively, this is a finite number of sum of omega and omega prime evaluated elements in M, right? But now you have to restrict to those elements in M1, so you're taking the soup over the smaller set. Therefore, it's decreasing. Okay, so that's the immediate consequence of the definition. Okay, another example I also like very much. In fact, sometimes you have to use this argument is that, in fact, when you compute relative entropy in quantum field theory, you never really do this directly. So there's always some kind of approximation, and sometimes you're lucky you have some exact formula. So usually you do this. If you get increasing matter phenomenon subalgebras of M with property that this generate the whole phenomenon algebra, then it follows that if you compute the relative entropy restricted to this subalgebra, it will converge to this phenomenon entropy on this relative entropy on the phenomenon algebra itself. Okay, so let me say a few words about the proof, because the proof once again is straightforward. Okay, it's a consequence of the definition, if you wish. Okay, so let's see how we're supposed to prove this. So I know that this sequence, this is a non-negative number. This sequence of non-negative number is going to be increasing, right? Because of the monotonicity I'm mentioning here. So it's going to converge to something. Okay. So the question is I need to show it converges to S omega 1, S omega 2, right? So let's just use this definition. So if I use this formula to evaluate S omega 1, S omega 2, I have to take the soup over these things, right? Once again, this integral here is just the evaluation of the state omega prime on finite number of elements in the phenomenon algebra M, right? So if you take any of such elements, remember Mi, generates M in the end, right? So take any finite number of elements here, I can always find a sufficient large I, index I here, so that Mi approximate these elements, okay? So in particular, so in other words, this shows that this relative entropy, when restricted to Mi, can get arbitrarily close to any of these elements here. Okay, so then if you take the soup of this, of course, you get arbitrarily close to this one. So that shows the convergence. Okay? So I have these two examples demonstrate the power of Kosaki's formula. Okay, I think it's even though it doesn't look very pleasing in the very beginning with this two soup, but it's many of the properties of relative entropy are now built in. Okay, so it's a really nice formula, and also I like this very much because I actually use this in the proof. Improve some of the theorems I will state later on. Okay, all right, so. Yeah, so it's really hard to see any feedback from the audience. I'm just staring and looking at the screen, and anyway, but I guess that's the nature of things now. Okay, so I'm going to move on to the next one. So let's see how much time I have. So I think we started.
Yeah, we started late, so until 25.
Until 25, so about 17 minutes. Okay, all right, yeah. Thank you. Okay, so yeah, right. So yeah, there are a few other properties are listed here, but I think I will just ignore this now. Okay, so maybe I would like comments about type 3 factors. So we know for type 3 factors, phenomenon entropy is always infinite. Okay, which is in many cases mutual information is finite. Okay, so and then if you take the single limits, you can explore the singularities of phenomenon entropy from the mutual information. Okay, I should say that these formal properties of phenomenon entropy are actually useful improving properties of mutual information. Okay, and also I should say that because of this martingale property, you can see that you can actually do this computation. I mean, in the previous talk and probably before, we also have heard about the split property. So if your phenomenon algebra has this split property, you can always find increasing sequence of type 1 phenomenon algebras, right? In which case you can just compute this without worrying about type 3 factors. Okay, so that's why even though many of the computations in the literature, especially in the physics literature, about type 1 factors, but frequently to get the right result, right? Because of this this martingale property I'm mentioning here. but sometimes one has to be careful. The type 3 thing really is important sometimes. Okay. All right. So yeah. So let's move on. So grid nets and subnets. Right. So I guess I will skip this one, and I will just get on to the mutual information for the case of free fermions. Yeah, the formulation in the case of free fermions is slightly different from what Tom presented before. That's because this is mathematicians' way of looking at the free fermion. So this is the in physics language, this is like the Dirac C construction, and so we construct using creation operator, and we constructed the CR algebra out of this, and right. So these are the creation operator, and then we define a net. So net is associated with each interval of the circle, a phenomenon algebra. So this is the phenomenon algebra generated by all these creation operators, all these operators. So it's the self-adjoint, creation operator plus the self-adjoint. This generates a phenomenon algebra. This is what we're interested in. So this is so-called the net of algebras associated with free fermions. Okay, so let me quickly get to the mutual information. So the mutual information I want to compute is what you think it is. So you take the vacuum state. So I have two disjoint intervals. You take a vacuum state, and then you take this vacuum state restricted I1, I2 respectively. So then you take the tensor product of these two states. So the algebra we're interested in is actually the algebra generated by observables localized on I1, I2. Okay, don't worry about this little 2 here, because free fermion net it's not a local, right? So this is not the usual tensor product. This is a graded tensor product. But let's not worry about that. So you can define the mutual information. So in some sense, you're measuring the distance between the vacuum state and this, tensor product of two restricted states to I1, I2 respectively. So this is the quantity I want to compute. This is the quantity I mentioned at the very beginning about the measurement result. So we really want to compute this, okay? And the computation of this is surprisingly subtle. So I have quite a few transparency prepared for this. So you see that you use the theory of singular integrals. You use the convexity of this quantity in a surprising way. But anyway, so let me just at least flash the screen, and then I just go down to the theorem. Okay, so we actually struggle a lot with this result. There's so many technical details there, and but eventually we get this. This is the formula. So I define. So I state the theorem in much more general way. So not just for two intervals, but for any intervals as well. Okay, and this is the quantity that's defined associated to this interval, and this is the result. Okay? So the result is written in a way which is sort of suggestive of what I said before about bipartite system, right? So it's like the phenomenon entropy of the first region plus phenomenon entropy of the second region minus the phenomenon entropy associated with the union of these two regions. Okay, but of course you see this is the point I want to make. Perhaps yeah. So maybe 25. So I have about 12 minutes. So this is really a point I want to make. So yeah. So you see, this formula here looks very much like what you usually write for mutual information for bipartite system. So maybe I can go back to that. Well, I don't want to try that because I may not be able to come back to this screen. But anyway, so if you remember, for bipartite system, we have a formula like, the mutual information is phenomenon entropy associated to one region plus the phenomenon entropy associated to another region minus the phenomenon entropy associated with two regions, right? But you see, I mean, formally it looks very similar, but I have to say there's something very interesting going on here, because we know we're in the free fermion case, in the quantum field theory case. So that formula is literally you have infinity here, and minus infinity here, right? So that cannot be right. But you know what I find amazing here is that there is actually what I think you might call the regularized phenomenon entropy here. Okay, this is a finite quantity, right? There's no infinity whatsoever involved. I mean, there's infinity if one of these endpoints touch each other, right? But it's finite quantity, right? So if you wish this GI here, you can think of as something like a regularized phenomenon entropy. Okay? I mean, you know, there's some mirror image of phenomenon entropy there, but it's in this case, you know, formally looks very much like, you know, this. So it formally looks like, you know, the mutual information of for bipartite system where you just have two intervals. Okay, so this is what I think is a regularized entropy. Okay, but I want to point out that one has to be careful with this because this quantity is not always positive. Okay, so this regularized phenomenon entropy, you know, even though formally it plays some role like phenomenon entropy for the type 3 case, but it's, you know, is in some sense you can think of this, you have subtracted some infinity, so you know the result might not always be positive. Okay, but at least formally there's some similarities. In fact, you know, I think there are more things to explore about this regular entropy. I will mention something about this maybe later. Okay, so this is a theorem. This theorem implies the theorem I stated at the very beginning of the talk. Okay. All right, so let's see. Right, so yeah, so this is so some formal properties. So this is what I said before. So formal property, I think there's more things to be explored. I just mentioned before that GI, I think that's here, has some formal similarity with phenomenon entropy associated with this interval, even though, you know, literally that phenomenon entropy is infinity. This is like a regularized phenomenon entropy. And what I mean by formal property is that we're going to explore that similarity and see what kind of properties this GI satisfy. Okay, so let me quickly go through. So these are some formal properties. So especially for those of you who have seen this before, you can see that this formula here, in the case of your bipartite system, this is exactly the usual. So this GA here is exactly the usual phenomenon entropy. Okay, but now what I'm saying here is that even in this quantum field theory framework, you still have such a quantity, but with, you know, of course, with this carefully chosen GI. And this GI, in fact, in some, if you impose some natural conditions, is uniquely fixed by the system. Okay. Right. This is what I said, that, you know, for free fermions, this is uniquely fixed. Okay. So we're able to prove that this GI exists for a large class, right? For a large class of systems, and in fact, you know, the way we prove these properties is actually by exploring the split property. So we explore the property. So this, okay, so good job. So you see, I want to point to the way we prove this formal property. We actually do this using fine dimensional factors. So free fermion, of course, we know is split. So we can find increasing sequence of fine dimensional factors. And remember the martingale property I said before? So if I want to prove any of these properties, yes, you know, any of these properties, all I have to do is to prove this on the fine dimensional algebras, because I know in the limit it converges, right? But then when you go to fine dimensional algebras, you have exactly, you know, the usual, you know, this is, so this A and B and the associated with fine dimensional algebras, this is the usual mutual information formula. These are genuine phenomenon entropies. So when you do this, you prove a lot of formal properties. So I think this is rather interesting, even though, you know, or GA and N is only regularized, but, you know, some of the formal properties follow through rather amazingly. Okay. Anyway, so let's see. Yeah. Right. So yeah. So maybe I'll say a few words about the structure of the singularities I was mentioned before. that if you have this mutual information, if the interval touch each other, then you have singularities. So let me maybe present a result on that case. So here's a result which may be interesting. So here I got two intervals B and C. So here A1, A2. So they're non-overlapping. So the end interval B is epsilon distance away from the left endpoint of C, right? So you then look to it for the mutual information, and you pick up some singularity. So singularity is logarithm of epsilon plus O epsilon. And I want to draw your attention to this very interesting quantity out of this asymptotics. Okay, yeah. So I think you might see Tom's talk at the end. He extracts some very interesting even spectrum structure from the singularities. So this is similar, but of course different in details. Here we extract the logarithm, half of a logarithm of the global index of my conformal net. So this is the index which controls the representation theory of this net. So it's quite interesting. And one comment is that, right, so I mentioned before that this is related to the topological entropy discussed by Kataev and Pascal. Okay, and in fact, even with the right factor, because we have this additional factor of half, and in Prescott and Kataev, they don't have this factor of half because, well, we have this half because we are talking about chiral half. Okay, so there are lots of similarities, but I think the relations of the topological entropy is largely unexplored. Okay. So I guess let's see what. Right. So I think I will skip this section, and I will go to this duality here. Okay. So I want to at least present a result, sort of more recent result on this on the investigation of relative entropy and so forth. So here's the result I want to present. So I'm taking two intervals on circle, so I1, I2, and its complement. And so its complement is the disjoint union of two intervals. And here's the formula. So here's the relative entropy. So omega J1, omega J2, these are the vacuum state restricted to J1 and J2, and you take the tensor product. Okay? This is the relative entropy. This like mutual information before. And here's the this is the relative entropy related to the complement of this region, right? And C is the central charge, eta is the cross ratio, and here is another relative entropy. So perhaps, I mean, if this is familiar to most of you, this is it's probably less familiar. So let me explain what this quantity is. So F here, Fi here, is condition from the larger von Neumann algebra to the smaller von Neumann algebra. Okay. This is a conditional expectation which wasn't in sectors such as disjoint intervals. Okay, and what is this omega composed with Fi? Well, you have a conditional expectation from this larger algebra to the smaller algebra. So using this conditional expectation, you can define a state omega composed with Fi on this larger von Neumann algebra. So that's that state, and we're taking the relative entropy between these two states on this larger algebra. Okay, so this is a relation I find quite amazing. Okay, we got three relative entropies, and you see the central charge of the theory appears, and here you have logarithm of mu a, which mu a is, remember once again, is the global index of the net. So you have the central charge and global index all appearing in the same identity. Okay. For those of us who have worked on conformal field theory for quite some time, there's one case where you see central charge and global index appearing in the same equation, right? That's the modular transformation of the characters. In that case, you will see that appearing in the same equation. But here we see that, this involves the relative entropy, the three of them, okay? So I find this quite amazing. Okay, this identity was discovered, was motivated by investigation of, the duality I was mentioning before, but I skipped that. But this is the one of the identities following from that investigation, which I find quite amazing. One thing, for instance, because relative entropy is always non-negative, you immediately get some inequalities. So here's an inequality which I find quite interesting, and you know, the only way to prove this is by looking at identities. So you just use the fact that the relative entropy is non-negative, you get an inequality like this. Okay, there's a lower bound minus half logarithm mu8, there's the upper half, and this one is also monotonically increasing in interval I. This is a result which is already quite non-trivial. Okay, because you might think it follows immediately from the monotonicity of these two relative entropies, but you know, one is, you know, this one is actually, you know, as I increase, this one increase. So you're subtracting something increasing, it doesn't follow that this is going to be increasing. But you know, the secret here is that this logarithm of eta cancel that part. But this can only be seen from the inequality I just presented. Okay. So I think my time is up, so I'm going to stop here. Thanks for listening.
Thank you for your very interesting talk. So are there questions or comments?
Maybe I will ask I Feng, very nice talk. Do
Hi,
you
Vergata.
have something in a higher space-time dimension of a inequality like this?
Can you repeat your question?
Do you have something that generalized to higher space-time?
Yes, absolutely. So this is true in the high dimensional case as well. So for instance, the same equation holds true for the full Cairo theory. So that would be on the two-dimensional Euclidean space. Yeah, and the same proof also works in the high dimensional case. But the problem with high dimensional case is that usually this logarithm of mu a is always zero, is 1. So this part is 0, right? But you still have this inequality here. Okay. Actually, wait, let's see. I don't know what the central charge is in that context. So yeah, so I can only say this is true also for the full CFD in two-dimensional Minkowski spacetime. When you put the left and the right together, this is also true. Okay. In that case, the central charge will be C plus C bar, okay? The left mover and the right mover. Okay. But in high dimensional case, I don't know what this quantity may be.
Also, mu index can be larger than 1, also in higher dimension. It depends on how you define it. But if you have some non-trivial superselection structure, then it is larger.
Yes, absolutely, yes. Yeah, you're right. I'm thinking about, you know, when you so what I have in mind is yes, you're absolutely right. So even in the full CFT theory, this you know, I mean, unless it's modularly invariant, this might not be 1. Yeah, this might be greater than 1. Yes.
Okay, are there other questions? Remarks?
So I lost maybe this point, this high Feng.
Hello, Sebastian.
So now this chain related, what? So it is a subnet.
Yeah.
But with the same central charge. So this central charge is our.
Yes. The central charge is
with the same central charges.
Yes, absolutely. Yes, you're asking. Yes, that's a very good question. It's a challenge to go beyond what, you know. Yeah. So Sebastian was asking about the assumptions about this identity. I mean, we expect this to be true in general, but the theorem stated in my paper is that it only works on the technical conditions. So it's all built on the result or free fermion result. Okay. So the central charge in this case is R. So it's integer. So it's a challenge to go beyond. Yes. So it's a challenge to go beyond what's stated in you know, to improve that assumption. So I expect this to be true in general, but you know, so far.
So if you take a subnet which different central charge. So with non-trivial coset, you don't know.
Well, if you, yeah,
so you get
well,
much.
you do know for the subnet, yes, but for the subnet you have to add a subnet and this coset. Then this is true.
Okay. Sure.
But the problem is you don't know separately if they're true or not.
You cannot
separate
them.
Yes. So that's still another issue. Yes. But one thing which is I think quite amazing is that this is true for all lattice theories. This is true for all lattice models because all lattices satisfy the technical conditions I mentioned before.
Yes.
So that's a huge collection already.
Yes.
Okay, other question? Comment? So please.
Hello, can you hear me?
Yes.
Yes.
Okay, so you mentioned in your talk about the concept of topological entropy. I'm wondering if there is any connection with the concept of topological order, which is quite fashionable in some corners of mathematical physics. And I think it also has some characterization, on the one hand, using entropy, on the other hand, has something to do with inequivalence of representations and sectors. So can you elaborate a bit more on this topological entropy, Kitaev, and I mean this stuff?
Yeah, I can say a few words, but the mathematical content is not as good as the identities I just presented here. But anyway, so yes, absolutely. So the topological order is because the fact that the global index is non-trivial. By non-trivial, I mean bigger than 1. Is related to the existence of superselection sectors. So that's where this what they call they have non-trivial ground states and so forth. Yeah, these are. I mean, in words, they all seem to be very reasonable and they're related. I am sure they're related. But I guess for us, the challenge is really to turn these things into some kind of statement, mathematical statement. And so far, I have looked at the paper by Kitaev and Presco very carefully. But unfortunately, I was not able to follow the argument. It's very hand-waving argument, but then the magic number come up in the end. So I don't know. I mean, I think it's a really interesting question to try to to look into the literature on this topological order and quantum computation and so forth, and see if there are any connections. One thing I want to point out though, most of the literature on this stuff, it's like they're doing this on sometimes on lattices, sometimes. But my impression is that this quantum information theory aspect is mostly on the finite dimensional algebras, finite dimensional lattices, and so forth. Okay, so here we actually start with a quantum field theory, and in the end we take some kind of singular limit. We realize that's the case. So it's not. I mean, there's some seems to be related, but one cannot really point a finger at where that's related, except that some of the quantities showed up at the end. So yeah, so it's a bit frustrating, I have to say.
Okay, I see. Thank you.
Any further comment? So if there are no any other comments or questions, so let's thank the speaker again.
Thank you.
Thank you for So we resume tomorrow. The first speaker is Daniela Gadamuro, and okay, so see you. Thank you for the
talk. Can I ask a question? So are the videos will be available, right?
Sure, at some point.
Okay, yeah, because I cannot attend some of the lectures because of I'm in a different time zone. So.
Okay, don't worry. So that will be on YouTube at some point.
All right, thank you.
Thank you.
So bye, everyone. Bye.
Bye.